So Alonso asked me to do a more hands-on session on the tools I showed you yesterday, and I figured it's quite hard to do it and being entertaining. And since I want to go in the code and how to use the tool, so I would like the session to be more interactive, if you will. There's 2 microphones in the front, so stop me anywhere when I'm going through the code and to the software, and just ask questions. If I don't have time to go through all the slides, it's fine. I mean, we will do what we can. Well, I do it what I can in 1 hour and see them. So please stop me whenever you want. So I want to go through 4 libraries that I use in the experiment I showed yesterday. DIPI is the big software library for diffusion imaging. Commit, which was the last part I showed with the streamline. Amico for the local voxel-wise microstructure estimation. And then the white matter query language, which was, I didn't explain directly yesterday, but was behind many of the figures that I showed you yesterday. So with those 4 software, you can do almost all the experiment I showed yesterday, and all those tools are open source and available. So let's start with DIPI. So you can go on dipi.org and have a look at the software. So it's an international project. A lot of people, a lot of lab, a lot of countries are involved in that, and the goal is to share state-of-the-art code and expertise in diffusion MRI. So people in the group, the DIPI organization are very responsive if you need help with the software development, and you can of course put yourself, start developing in DIPI as well. So DIPI is really focusing on diffusion imaging, but it's part of a bigger community which do essentially neuroimaging. But DIPI is maybe the biggest project. So let's start. DIPI was founded by Eleftherios Garifalidis during his PhD, and after the PhD, the project started growing, and a lot of people got involved over the years. You might recognize some faces from CIMAT. So there's today about more than 60 contributors to the project from many countries, and the project is growing and growing. So people get involved, and the project is getting very big. Also, some industries start using DIPI, which is good for the visibility of the tool that we develop and to get feedback from the industry. And also, DIPI is supported by different grants. And maybe one of them interesting is the Google Summer of Code. I don't know if in 2018 there will be a proposal, but if you are interested to learn about diffusion MRI or get involved in software development for a few months, this probably keep an eye on that. It might be it might appear soon for the next year. Get some. So if you go on dipi.org, you have all the documentation. You can go on the Gitter to get a chat room to discuss with the developer. The code is on GitHub, and everything is there. And the most important part is the tutorials or the example on dipi.org. And essentially today I will go through many of those tutorials just to show what DIPI can do. But there's a lot of documentation, and I think it's the best way to learn the platform and also learn about diffusion MRI, as many things are there. So to get DIPI installed, you need to essentially follow the instruction. It's very easy. You can, if you have Python installed on your computer, pip install DIPI, and you're ready to go. So very simple to get started with DIPI. So as I said today, I just want to show some of the tutorials that I found quite interesting and related to the talk of yesterday. So just before I start, who has ever worked with DIPI? Nobody? Who's doing a bit of Python? Do you know about Python? Maybe 10, 15 people. Okay, so it might be a bit overwhelming with all the line of code. I try to keep it very simple and just give you the idea, but if you don't get exactly what the line make, just try to figure out the amount of code that is needed to produce the result. And also, it's not like FSL or Matrix as you just run commands. You really need to write your own script, but it's more for software developer, I would say, than neuroscientists at this time. But on the other hand, you control every parameters and you know exactly what you are doing, and it's then easy to extend and build upon the current code that is there. So just to get started, we need some images. So this is just an example of a path to get to the diffusion images, and we have the BVEC and the BVAL file that describe the diffusion sequence. So to load those images, we have the nibabel library, which we can do nibabel, nib.load the diffusion images, and then we can get the data. And data is just an array of the size of the image by 160 in this case, which is the number of diffusion-weighted images. So just simply like that, we have an array. If you don't have any images yourself, this could be your data, but you can get example data from DIPy if you just run this example, this piece of actually, sorry, this is to get the gradient table. Now, with this line, you create essentially the gradient table that describes the diffusion data, so you can use it then to process the DWI. But if you don't have the data, this is the line, you can use the data from DIPy. So this is in the, you don't need to remember any of that, as this is the first part of any of the tutorial in DIPy. So you get the data, it can be yours, or it can be data from the example. But at this point, you have an object that describes the data, and you have an array that contains essentially the data. So the first thing you might want to do is diffusion tensor reconstruction. So to speed up the process, in DIPy you can call the function that is called median otsu, which essentially take the brain out of your images. So essentially you remove everything that is outside the brain, so you will compute the diffusion tensor only in the voxel. This is not required, but it's something that will speed up your computation. So then if you look at the shape of your original data, which was the size XYZ of the image, the number of diffusion-weighted images, the shape of the mask is just the brain, so just a 3D image, and the shape of the mask data is the same size as the original data, but this time everything outside the brain is 0. So if you want, now you have the data, you're ready to compute the diffusion tensor. So you need to set the model. In DIPy, everything is in the package recons. There's many other models, but you import the package DTI. You define your model, the tensor model, giving your, the description of your diffusion images, and then you fit the model. So at this point, you have the tensor fit. This may take a few seconds, up to maybe a minute to get the result. But then, once you have your tensor, essentially you have your image of tensor, you can compute all the tensor metric that you used to. So for instance, to get the FA, you take your fit and you get the eigenvalue of the tensor. And this, from the eigenvalue of the tensor fit, you can compute the FA. And if you do that, you have an image in Python that is the FA, and you can save it using the nibabel library. If you do that, you save the nifty on the disk. You can then load it in any software and start playing with it. So very easily, you load the data, you define the model, and then you compute the metric from the model, and you can save the images and start playing with that. So in a very similar way, you can compute, for instance, the mean diffusivity from your tensor fit.md, and then you save the image, and you can display it in any software that load the nifties. Or again, the color FA will be in a few lines, you can get those images from the tensor model. So this is maybe the first thing you would like to do with your diffusion images, looking that the FA look fine, the MD is also good. You can look at your orientation to be sure that there's no flip in your data. Maybe a first way to look at that your image look good. You can also look at the tensor model itself, the ellipsoid. In DIPy, there's a visualization package that is called FVTK. So it's essentially a wrapper over VTK, the visualization platform. So you need to get something ready, for instance, a discrete sphere where you will project the tensor or the ODF. But essentially, if you use the function vtk.tensor, which is essentially the visualization part of FVTK for the ellipsoid, you put the eigenvalue and the eigenvector of the tensor, and you can display some part. For instance, here it's just a part in the kernel slice of the corpus callosum going this way, and the CST going up like this. So you can look again at your data, do some visualization, and be sure that everything looks good. You could also save those features and use it in another software or in a different tracking algorithm or what you want. If you use the function vtk.peaks and you give the eigenvector, the first eigenvector of the tensor, you will get the main direction of the tensor. Again, that might be useful for your local estimation or to look at your data, essentially. So now, if you want to move on to CSD, for instance, you will do something that is very similar to the tensor estimation. You need to import, the first thing you need to do for CSD is to get a response function. So if you remember, with CSD, we model the diffusion signal as a convolution between some response times the true fiber orientation distribution. So you need to have this response, and one way to do it is to get it from the data. So this function will essentially look at the central part of your image at the value, at the voxel where the FA is greater than 0.7, which is usually the value that is used in matrix, for instance. And so in this way, you get an object which is the response function, and you can use this piece of code to look at it. So the response function looks like this, the UDF of the response function, actually. So in one line of code, you get the response, which you need for CSD. And then in a very similar way that we define the tensor model, we define the constraint spherical deconvolution model. So recons.csd, and we define the model with the gradient table for the data and the response that we just estimated. And then we call the fit function with the data. And at this point, we have, this will be a bit longer than a tensor, maybe, I don't know, 10 minutes. And you will get your CSD model fit to your data. So if you do that, you can, for instance, look at the ODF. So you have your fit. It's an array. So you can, here is the subset of the array just for the display. And again, you have the corpus callosum going up here, the CST going up here, and you see very well the crossing between the two fascicles. So again, in 3, 4, 5 line of code, you have your response function, you have your data, you have your fit, and you can get the ODF. And if you look at the object CSD ODF, it's an object that is 10 by 10 for the image, so 10 voxel by 10 voxel by 1 by 724, which is the number of points on the sphere that you project the spherical harmonics to get this ODF. And again, DIPy offers some visualization tool for the ODF, which might be very useful. This is a 3D view, so you can play with that with the view in the code. So if you would like to get the peaks of the ODF, for instance, for tractography, or to look at the number of peaks in every voxel, or if you want to use the peaks for fitting some other model, you can call the function which is called peaks from model, which define the model that you want, the data, the resolution of the sphere, and many other parameters that you can look at. But in the end, with this, you can extract the peak and the direction, and you have, again, your corpus callosum and your CST going up, and the peaks from the ODF. So very few lines of code to get access to this in DIPy. If you want to use the spherical harmonics, for instance, when you run it from a matrix, you will get a nifty file with the spherical harmonics. You can take your object that you just fit, take the spherical harmonics out of the object and save it as a nifty file, and use it in other software other algorithms. So that was for the local estimation, the local modeling part of the signal. So the tensor, the CSD, there's many others you will see. But now if you want to do tractography, the first thing that you might want to do is to define a simple mask from the diffusion images. So in DIPI, the mask or the classes of mask are called the tissue classifier, which is a general type of class, but the simplest one is the threshold tissue classifier, which take as input your FA and a threshold on the FA. Typically 0.1, 0.2 will give you a good mask of the white matter in which you can run tractography. So for instance, this is the mask of the FA thresholded at 0.15. So you could use that for tractography, for instance. So if you would like to do, as I did in the presentation yesterday, and use the T1 to define the mask, you first need to provide or to have the partial volume estimation. So the PVEs, partial volume estimation of the white matter, the gray matter, and the CSF. So this is the path to the file. Again, you use nibabel to load those files. And now you have an array containing the data. Or you can get some example from DIPI if you don't have the images. So if we look at those images, if we just open the Nifty in the visualization software, we see the partial volume fraction of white matter, of gray matter, and of CSF. And this is what we want to use to define the mask for tractography. The first thing you might want to do with those partial volume fraction is maybe to look at the binary tissue classifier, which essentially take every value of the partial volume fraction map of white matter that are greater than 0, and this become your white matter mask for tractography. If you want to do like yesterday and use either the CMC algorithm, which is the probability based on the partial volume fraction, you can define it, or the ACT tissue classifier is very, very similar, that you can define it from the 3 partial volume fraction. You need to provide additional parameters like the step size for tractography and the average voxel size of the image. But this way, you have a tissue classifier that can tell you the streamline stop in the white matter, stop in the gray matter, stop in the CSF, and you can do something else out of it. For this algorithm, the way the probability are defined is based on the step size of tractography. I didn't show it yesterday, but if the step size is, you have a probability of going through the voxel with CMC that is proportional to the partial volume fraction. So if the step size is very short, you want that the amount of streamline going through the voxel stay the same no matter what is the step size, and this should be proportional to the fraction of white matter. So you can correct the probability based on the voxel size and the step size. And if you look at the actual map, this is the inclusion map, so everywhere in this volume, it's fine for tractography to stop, which it is essentially the gray matter plus the outside of the brain, because we want to keep the streamline that go down the brain stem and exit the image. So we want to keep those streamline. The exclusion map, which is the region that we don't want tractography to stop, is essentially the CSF. So you don't want tractography to stop in CSF because it's not anatomically plausible to the white matter the axon shouldn't start from the cortex and stop in the ventricle, for instance. It shouldn't go through the ventricle either. No. So yes, because with this, essentially, there's no streamline that will go ever in a voxel containing pure CSF. But if there's a fraction of CSF and a fraction of white matter, you will allow the tractography to go to some extent, but you will penalize tractography with the particle filter, for instance. So there's no way streamline will go through the ventricle. They might go on the boundary if necessary, but you absolutely don't want to keep streamline that stop in the CSF. You want those that connect the gray matter, and don't stop in the white matter either. At least for an healthy brain, you don't want the axon or the streamline that represent the axon to stop in the white matter. So to do a simple tractography algorithm from the corpus callosum, for instance, you can get a label map like the one that you could get from Presurfer. And here the label 2 corresponds to this central sagittal slice of the corpus callosum. So just a way to place some seeds in the volume. So here, seeds is a list of 3D position where you start tractography. So there's many ways to define the seeds. One way is to provide a label and put some numbers of 3D position in every voxel of the label. So now we have the seed, we have the mask, we have the local reconstruction from CSD, for instance. Now we can run tractography. So in DIPy, there's a few tracking algorithms. We call them the direction getter, essentially, which is the way to pick the next direction, giving the propagation of the streamline. And so you need to provide the coefficient of the spherical harmonics for your CSD, for instance, which defines the profile of the fiber orientation. You define the max angle for tractography, and some other parameters like the resolution of the sphere. So we call this the probabilistic direction getters. Is the algorithm that I showed yesterday, where you sample the FOD based on the amplitude of the lobe. So more the value is higher of the CSD, more likely you draw this direction for tractography. You can also define a deterministic direction getter, which essentially will take the maximum of the distribution of the FOD. So we take always the peaks of the CSD. There's another algorithm in DIPy, it's called EUDX, which track on the peaks. So if you have a local model and you can extract the direction of the fibers, or you take the peaks from the CSD, you can provide this object, which is the peak from model, the object that is returned by this function, and use that as a direction getter in DIPy. So this is an abstract object for tractography as well. So essentially here you can define 3 different tractography algorithm, and then you can run tractography with this function, which is called local tracking. It takes your direction getter to know which direction to follow. It takes your classifier, which is essentially your mask, the seed position from which to run tractography, and few other parameters of the image, or the maximum length of the streamline, for instance. And once you define this object, you can save it as a TRK file, which would be your streamlines. So again, probabilistic direction getter, deterministic direction getter, and then you run this local tracking function to get the streamlines. Yes?
So the number of streamlines is determined by the number of seeds you have. You can find it in the opposite way, if you want to have the numbers of streamlines.
In DIPy, you cannot do that. You cannot say, I want 1,000 streamline. What you will do is to track 2,000, put 2,000 seeds and subsample to 1,000 streamline. Also, depending on the way, if you set the parameters return al, essentially you will have 1 streamline per seed, which makes sense. You place a seed, you look how far you can reach following the direction of the CSD, for instance, and then you save this line. If you put these parameters to false, then this is the tissue classifier that will tell you tell the local tracking algorithm if the streamline should be returned or not. So essentially, by putting these parameters to false, you will only have streamline that connect the gray matter in the end. Every other streamline will be discarded. So then, if you put 1,000 seeds, you might end up with 700 streamline, for instance. So if you want to do the particle filtering tractography that I showed yesterday, to recover more streamline, you can call this particle filtering tractography instead of the local tracking function. So it's very, very much the same. The way you pick the direction, the mask, the seeds for tractography, few other parameters, for instance, the number of particles you use, the number of sample, the distance you backtrack, the distance you go further than the distance you stop. So you control everything here, and then you can run it in a very similar way. And this is not in the DIPy master branch yet. The code is to be reviewed and be put in soon, I guess. So when you're done with the streamline, you save the TRK, and you can use your favorite software to look at the streamline and get your reconstruction. One thing you can do once you get the streamline, in DIPy there's the quick bundle clustering algorithm. So this is your original tractogram, and quick bundle try to find the centroid that better match the distribution of your streamline, the original streamline. So as the algorithm move on, it find the centroid which match the streamline, and then if the distance is under a fixed threshold, it put the streamline together, and what you see here is the central part of the bundle, and this is the full bundle with all the streamline associated to it. So this way you can simplify your big set of streamline that you computed by a subset of centroid that approximate your connectivity.
Is that the Eleftherios Garibaldi's algorithm?
Yes, this is the quick bundle algorithm. So this way, it's an automatic way to group your streamline that look alike, that are spatially close and have a similar shape. So given your initial set of streamline, you get the centroid and you get the cluster, and this could be used, for instance, for analysis of the data. And so this is very data-driven, as you don't define the centroid before, but you build this centroid based on the tracks that you have. Yes?
Can you provide the cluster, say, derived from an atlas, and have a new subject and say, classify these streamlines according to those centroids?
There's a paper that came out this year, I think, that is called Rico Bundle, that essentially is built on top of Quick Bundle, which use a dictionary of clusters. So you have your, say, high resolution filter cluster that you manually identify on one of your subject or from a database, or you have something that you think it's interesting bundle that have anatomical labels, and then you find a streamline that best match those. So you have you put the labels from your dictionary on top of the streamline that you have. And this is built on top of Quick Bundle. And I think it is available in DIPy. I never used it, but if you look, there's example, I think, for Rico Bundle.
And a similar question, if, say you're in this case where your own tractogram starts to find the clusters, can you find the weight or the distance of a particular streamline to any given cluster, and that way remove any lines that are really not that?
You have access to this information, but the way the algorithm works is you fix a distance, and actually the distance that is used is called the MDF distance, which the way it's computed is take every streamline from, actually take the centroid, the streamline of the centroid, and compute the distance point to point with the same the streamline are resample, for instance, with 10 or 20 points, and then you compute the mean distance. If this distance is below a threshold, you put the streamline in this cluster. If there's no centroid that is close enough, you take the streamline and this becomes the new cluster. So iteratively, you add new centroid as the streamline are different, and you group them based on this distance. And this, you control the value, the maximum value. So you know at the end, the maximum value in the cluster is below this threshold. But you could refine the cluster afterward and put a smaller, say, kind of hierarchical clustering where you put a big value at the beginning, you get 20 cluster, and then you take each cluster and you subdivide, reducing the distance and so on, and you can build a 3D. There's a piece of code also in DIPy that do this kind of approach to the clustering problem. Yes? It will become many bundles. It really use only the spatial distances between the lines. So if, for instance, if you have a group of streamline connecting very in a U shape, the top to of both hemisphere, and you have at the same place but connecting the lateral side of the brain, you will have two clusters here. And then based on your threshold, you will have several clusters going from the front to the bottom, to the back. So you don't know how many clusters you will get, but it will be driven by the data, the way the number of clusters that you get. Yeah, but this is because in the original tractogram, we don't have much of those connections on the side. If you would have it, most likely you will have cluster for those. Also, what a very interesting thing is some colleagues use this technique to find the cluster that contain almost no other streamline. So they are alone in their space and shape, and then you can think that those streamlines are maybe invalid connection and throw them away. So if there's only one line that has one shape in one area of the brain, it's a bit suspicious on the reproducibility or the validity of this set of streamline in the brain. And so you can use this kind of density analysis to figure out which streamline are more likely to be there or not. Something that have been built on top again of this algorithm. I didn't discuss this yesterday, but it's related to probably some of your project. And it's about microstructure. I don't know if some of you know the map MRI modeling technique. It's very interesting as it essentially tries to model the diffusion signal, but in 3D. So if you will, it's like try to fit spherical harmonics, but instead of fitting it on one shell, you try to fit the 3D diffusion signal. So if you have the diffusion signal on several shells in the Q space, you can try to get to fit this model, and then you can resample the diffusion signal wherever you want in the Q space. So it's kind of, you get a continuous representation of the signal once you fit this model. So I will just go quickly through the equation. It's not my work, but I found it very interesting. So you model the signal here in the Q space as a sum of weighted functions. So the goal will be to find the coefficient of those functions, but you have a set of functions for some fixed order of the basis. And then each of these functions is the product of one 1D function in x, y, z. Okay? And there's a scaling parameters of the basis to the data that can be either fixed or estimated from the data. And then you use the MapMRI technique use the Hermite polynomial as a basis, as a 1D basis for the signal. So it's not a big deal, but it's just the idea that you build a functional basis to represent your signal in the Q space. And once you fit this function, you can resample at any points in the Q space with that fitted basis. So in DiPi, again, it's the same as the tensor or the CSD. You need to get your data. You need multi-shell data or DSI data. You need multiple, you need points that are spread a bit in the Q space. Otherwise, your basis function won't well represent the data. So you need this work only if you have a single diffusion time. So you need to tell the fitting algorithm that your big delta and small data for the diffusion acquisition. Otherwise, the value you will get won't be representative of what it actually is. So this fitting of MapMRI is very long compared to CSD. So why here I just took a single slice of the brain and a middle sagittal slice. So you do the same. You define the MapMRI model as the tensor of the CSD. You give the information on your diffusion images. You define the radial order. These are the parameters of the fitting and the regularization parameters for the MapMRI model. And if you do that, then you fit the data, and you can save many of the MapMRI parameters that you might know. Here, we'll just go through three of them, which is the mean square displacement. So this is a value that tells you how far the water molecule are able to diffuse in the brain. So this is a scalar value that tells you locally in every voxel, on average, how far the water molecule diffuse in 3D. We have the Q space invariance matrix, which again it's an estimate of the variance in the diffusion signal. And you can see that the variance is a very low in the white matter and very high in the CSF or in the gray matter. So get information on the tissue. And maybe one last is the R-top metric, which quantify the probability that a water molecule return at this origin position between the two diffusion poles. So just a way to get metrics out of the modeling of your signal. And there's many others if you want to look at the MapMRI paper, and most of them are implemented in DIPI. Also, if you fit the signal and you have a continuous representation of the diffusion signal, you can resample the signal on the grid, for instance, and you could compute the EAP, or you can do whatever you want, essentially. Of course, the difficult part is the fitting, and your data must be good enough to be able to fit with this basis function. But when you get it, you can do many, many things. Yeah, for instance, you can compute the ODF out of the MapMRI fitting for one slice. You could resample the signal, for instance, on one shell, be 2000, and then you compute CSD out of the resample signal. For instance, if you have a weird acquisition scheme where it was not suited for CSD, you can fit MapMRI, resample the signal on one shell, fit CSD, and get the fiber ODF, for instance. So there are many, many, many other things in DIPI: pre-processing algorithm, local reconstruction techniques, registration tools, segmentation, fiber tractography. I went mostly through those two. Streamline evaluation, computation of connectivity metrics, and so on. Some visualization tool as well. So there's many things to look at. All of those techniques have tutorials on the website. You can look at it. It's a good way to learn those techniques and to see if you want to add something else or compute something out of those. For instance, local reconstruction, everything is there to learn and to use. I don't know if you have some question now before I move to Amico. Is it? I'm not. I know the paper is out. I don't know if all the code is there. I would have to look, but if you communicate with the author of the paper, for sure he will be able to share his code. I know the guy. If it's not in DIPI, it's his work on the way. It will be there at some point. Yes. No, but I mean, you need to if you use the diffusion images, it doesn't matter which space or which voxel size you have, or it essentially work with the 3D or the 4D matrix of the data. If you want to, for instance, have the T1 information on top of your diffusion images, then you need to be sure that the images are registered. So either spatially registered or the same resolution, but you need to be sure that the data are spatially coherent. Yes?
Very initial pre-processing steps, can they also be done, such as the
There's a few. Mostly now denoising. I don't think there's bias correction and eddy current correction yet. Something that will get there, I'm pretty sure, in the coming years, for instance. But I think yet you still need to use, for instance, FSL to do this kind of thing before getting the data into DIPI. But it will get there, I'm sure, at some point. The plan is to do also that. But as you see, the local reconstruction part is very, very good in DIPI. A lot of technique, probably the software that has the most together. And once if you want to compare this technique in some way or get scatter value out of this technique, you can do it very, very easily, where you just essentially declare all your models, fit them, and get the value. You know that you're in the same space, in the same framework, and this might be very useful. So again, I'll move on to Amico. So Amico is a project that Alessandro Daducci started in 2013, 2014. This is the tool I use for the extract algorithm to estimate the axon diameter index. So essentially, it was basic tractography, but at each step I was calling Amico to get the microstructure information along the peaks. So again, everything is on GitHub, very easy to install if you follow the simple installation steps. So we'll go through two examples. The two examples are on the website, on the GitHub, so you don't need, I mean, you can do it yourself afterward if you want to get used to, and then you can swap the example data with your own data and see what you can estimate. So Amico needs a special folder structure with the diffusion images in a study folder and a subject folder, and then the diffusion images and the diffusion scheme for the data in this structure. You will see it on the website. It's the way the code is structured. And from the study 2, which was the parent folder here, if you open a IPython terminal, which is a console to write Python code, essentially, you can first import Amico, like this, and then you call this first function, which will essentially just initial the Amico framework, giving your position on the disk. So you set the parent folder, the subject that you are interested in, and then you tell you tell Amico which are the diffusion images file, which is the scheme, the acquisition scheme, and the mask if you want to compute Amico on the brain or on the white matter only, for instance. So with this, you load the data, you set up Amico, you load the data. Amico tried to fit a set of kernels to your data. So you need to define which model you want to use. So yesterday in Extract, I was using the Cylinder Zeppelin ball model. You can set the parameters of those models if you want, but in this case, I use the default. And then I asked to compute the kernels, so the kernels that I want to fit afterward on the data. So this load kernel function will generate kernels, will generate the kernels in high resolution, and the load data will project those kernels on the diffusion scheme that you use for your subject. So just a way to do that. And then you call the fit function. So in this case, it fit the Cylinder Zeppelin ball model to a subset of voxel, 200 voxel in 6 seconds. And then you can save the result. Save the result for this model. Each model have a set of images that are the result of the fitting. And with this Cylinder Zeppelin ball model, you have the axon diameter and the fiber density. So here it was, the data was ex vivo monkey, the one I showed yesterday. And this is the original ActiveAx model, and this is the one fitted with Amico. And you can look at the fiber density and the axon diameter index that you estimate. Here it was only a single fiber population, so the diameter is an estimate of the diameter in this direction. Actually, I was confused because there's a typo. Here's not the ActiveAx model, but it's the NODI model. So you might be interested by the NODI model at some point for your diffusion data. Actually, I was confused. This is the NODI slice. So in this case, this is the other example. In the same way that we did earlier, you structure your data in a study folder and a subject folder. You start your IPython terminal in the folder, and then you initialize the framework. You define the study, the subject, and in this case, we needed to convert the bval and bvec to a scheme file, which is the format that Amico uses for the diffusion images. So same thing as earlier, image, protocol, diffusion protocol, mask. We load the data, and now we are ready to compute the response function, but this case with the NODI model. We load the kernel for the subject diffusion scheme, and then we fit the model to, in this case, 5,000 voxels in a few seconds. And this gave us a set of images that we can look at afterward. So again, this is the original NODI from the paper. There's three metric, the isotropic volume fraction, the intracellular volume fraction, and the orientation dispersion, which are estimated with this model. So you can see, for instance, here that the NODI amico is very similar to the regular one when you don't apply regularization. But if you do apply regularization in the fitting, the maps look even more smooth than the original NODI model. So you can get this map, as you said, you saw, very simply, few line of code. You just have to put to have the data and the diffusion scheme, and you can compute those maps. Of course, for NODI, for instance, you need data with at least 2 shells to be able to compute them. But if you have those data, you can run amico. So do you have some question on amico and the fitting of those models?
No, let's use it because we are recording.
Okay. Amico was first developed for MATLAB, and that's the one I had used.
Yes.
Is it still maintained, or has everything been translated to Python, and I should?
Yeah, the MATLAB version is not maintained anymore. It is on the GitHub. So if you the original paper, if you want to do the experiment of the original paper with the same implementation, everything is there. But it's fixed in time. It's not. Okay. If you want to develop it, it's up to you. I mean, the code is there. But the Python version is faster, and there was a bit of refactoring, so it's easier to use as well. Okay. And yeah, and then I show you two models, but you could extend this fitting the way you want. If you instead of fitting, for instance, cylinder, Zeppelin, and ball, you could fit just the Zeppelin and the ball, or just stick and ball, and you use some kind of ball and stick estimation. You define the way you save the weights into those kind of maps, and then you're good to go.
Say implementing Astro cylinders, is it already done? Can I just call for the model with Astro cylinders and ball, for example?
Good question. I don't think so, but I guess it will be pretty fast to do. I mean, you just have a way to compute the kernels. For instance, the cylinders and the Zeppelin and the ball is quite straightforward to compute. We have an analytical model for those. If you have something a bit more complex, you might need simulation for those type of compartment. But this is something that you can add and use the framework to then do the fitting. Essentially, amico is just a fitting framework giving a set of kernels. So you define the kernels the way you want, and then you use the mechanic of the framework to get the fitting, and then you extract whatever you want out of this fitting.
Thanks.
Any other questions? I think I have maybe just time for the other. I have until what, 11:15. So I can go quickly over commit, which is very similar to amico, as you will see. Okay. So again, commit is a software developed by Alessandro Daducci in 2014-15. This is the paper if you want to have a look. And this was the last part of my talk yesterday. Very simple to install as the other tools. So we do very similar thing as amico. We need the data. We need to put the data in a structure for amico, for commit. So in this case, we put the data in the Lausanne2 shell folder. We move there, and we start the IPython terminal. The first thing to do with commit is to build what in commit is called dictionary, which take the track file, the streamlines, and build essentially the set of intersection between the line and the voxel grid. So you know which streamline intersect which voxel, and you can use that in the computation. And you can fix some other parameters if you need. But once you get that, this can take a few maybe a minute or two, depending on the number of streamline that you have. You do the same thing as with amico, import commit, initial setup. You set your evaluation folder, in this case is Lausanne2 shell, DWI, diffusion scheme. You set the forward model as in amico. In this case, the stick, Zeppelin, and ball model. It could be the cylinder, Zeppelin, ball model, or ball and stick model. All of those models are there for a commit. You can set the parameters of those different compartments. Again, you can use the default if you want. You generate the kernels. You put the kernels in the diffusion space. So you sample the kernels on the same diffusion images that you acquired before. You load the dictionary. So this is the track dictionary, which intersect your 3D volume of voxels. So this is just some mechanics to be able to compute the matrix. Will be very, very huge, as you can imagine. You have maybe hundreds of thousands of streamline intersecting many hundreds of thousands of voxels. So this can be very, very big. So you need some kind of special mechanic to be able to do the matrix vector multiplication here. So now what you want to do is to fit the model, and it's essentially just calling the fit function there. You define the model, you get the data, you just run it very quickly. And similarly to Amico, you can save the result. In this case, for this model was the extracellular volume fraction, the isotropic, and the fiber density. So the fiber density, this is the fiber density that you will get from the original tractogram. So essentially, it's related to the number of fiber crossing every voxel. In this case, is the fiber density weighted by the weight of commit after the fitting. You can also get the extracellular contribution, in this case, the weight of the Zeppelin models in every voxel of the brain, and the isotropic contribution, as you see higher around the ventricles. In the end, you can also look at your error in the fitting, so the distance or the error between your signal and the signal you fitted with the set of streamline and the different compartment that you use. So you can look at it to be sure that there's no voxel that has ridiculously high fitting errors.
Sorry. So you expect that that map of error is around the value of the sigma of the noise, right? If you are doing everything well.
It should be in this range, yes.
But is that the case in a basic experiment? I guess no. Maybe you need to add more streamlines until you get that.
The number of streamline is a good question. As I said earlier, ideally, if you want to do a proper fit, you will need streamline that cover well all the volume, and you put a single weight per streamline, and the streamline cross hundreds of voxels. So somehow you have to have streamline that are real to be able to well explain the data. But as you have more streamline, the matrix becomes bigger. So there's a kind of balance between the amount of diffusion data you have, the amount of streamline that you need, and how well you want to approximate the signal. Do you have any other questions? Yes?
There is a specific limit for in the data that you can feed to CIMAT.
Mm-hmm.
Do you need a certain number of shells, directions, something?
For instance, if you want to fit diameters, you will need multiple shell at very high B values and high gradient. If you want to fit kind of tensor model or ball and stick, you can do it with a single shell. If you want to fit the Nodi model with the Nodi model, the ball and stick model, you will, a single shell will be enough to do that.
Thanks.
Of course, if you have more data, it's even better even for the simple model. But I think I will stop there. I have maybe 3 minutes. I don't know if I should go quickly over the next. Maybe just give you an idea that the tool exists. The tool is called, actually the idea is called the white matter query language. It's implemented in the track courier. But essentially, it allows you to define in a rigorous way what are the tracks in the brain. So you can define, you move quickly. You use logical operation to define, I want the streamline that goes in this label of free surfer and in this label of free surfer, does not go below or posterior to another labels, and you can build this way a definition, a strict definition of what a fascicle is, using these terms, and then you can define some kind of structure. For instance, the frontal lobe will be this set of labels. In free surfer, an hemisphere will be everything that is left in the free surfer label, the hemisphere left, and then you can start defining what the track is. If I jump to, and then you call this line with the parcellation from free surfer, your query that you have to define, and your streamline. So parcellation, streamlines. What's going on?
It's coming back.
And then, for instance, if you want to define a corticospinal tract, you might say, I want every streamline that goes through the precentral area and go to the brainstem, or go to the postcentral gyrus and through the brainstem, but does not go in the occipital lobe, does not go in the temporal lobe, or in the singular, or in the superior parietal, or does not go in the opposite hemisphere. So you define strict rules, and then you can get those kind of bundles that you extract automatically from the data. And on a single subject, it might seem tedious to do that, but if you have 20 or 30 or hundreds of subjects, you define this very carefully once, and then you can extract all the fascicles automatically afterwards. So if you want to define the articulate fasciculus, you might want the streamline endpoints in those labels, and again, you define some kind of constraint on the fascicle. Or you could, for instance, here, we want streamline that ends in the orbital frontal gyrus, ends in the temporal lobe, but also don't go posterior of the amygdala. And this way, we can get the eusinate fasciculus. Yeah, in very similar way, you can do that for hundreds of, tens of bundles. This is the way we define, if you remember yesterday, the mean value of the axon diameter index. The way we compute that is to extract the bundle on all the subjects using this kind of queries. So this might be very useful if you do group analysis. So again, it's very simple to get the tool working on your platform. Everything is in Python behind, but we have some script, in this case, to help you running the queries from your Atlas, Streamline, and data. I don't know if you have some quick question.
Yeah.
Before.
One question. That is the case. Otherwise, I think no. Okay.
All right.
Thank you very much, Gav. Very nice presentation.
Thank you.